Hello. I'm sorry to be only with you all virtually, but grateful for this chance to congratulate Peter and offer him good wishes for the next decade. I'm actually a year older than him, so I can assure him that being 80 needn't be too bad. Peter's a long-time friend and collaborator. We are both lucky in at least two ways. First, to have survived this long, when many of our friends and colleagues sadly have not. But second, to have been engaged with astrophysics throughout the last 50 years, an era when the subject's been on a roll, with ever wider developments leading to the vibrant multimessenger field that this conference is focusing on. So let's start with a bit of history. It's said that the Woodstock generation would not remember the 1960s because they weren't really there if they remembered it. But we oldies, whose involvement in astronomy goes back that far and who were able to remember it, were fortunate to witness really exhilarating progress. When the 1960s started, we had optical telescopes using photographic plates and not much else. The only other messenger that then was opening up was the radio band. And there was a debate about whether the universe had a beginning or had existed forever in the so-called steady state. And that debate was famously settled in 1965 by the discovery of the microwave background by Pennington and Wilson, which inaugurated cosmology as a real science. At about the same time came the discovery of quasars and active galactic nuclei. And this allowed even the then existing optical telescopes to probe back further into the past than was thought feasible when only normal galaxies were known. And it offered at least the intimations that massive black holes might exist. Another surprise was the 1967 discovery of pulsars, objects where relativity was crucial, not just a small correction to Newton as it is in normal stars and galaxies. Pulsars are neutron stars, exemplifying how we astronomers can actually contribute to basic physics by exploring and modeling situations far beyond anything can ever be achieved in the lab. And it was a fortunate coincidence that thanks to Penrose, Hawking, and their associates, this was the same era when theorists elucidated the properties of black holes in detail. It was at least a decade later, however, before the relevance of supermassive black holes to quasars became a consensus. That stayed controversial throughout the 1970s. The 1960s, of course, also witnessed the emergence of space astronomy, opening up most of the electromagnetic spectrum for observations, X-rays in particular. And Peter was lucky to become a graduate student at Berkeley and to learn about X-ray astronomy, which was crucial for highlighting locations of especially high energy activity. But Peter's PhD topic was the interstellar medium. He came from Argentina and from Hungary and Belgium before that. I believe English was the fourth language in which he became fluent. I first got to know him when he came as a postdoc to Cambridge in the early 1970s. He'd already begun working on neutron stars and strong magnetic fields. Indeed, this is a topic where he became a world leader. His contributions, in fact, culminated in a monograph published by Chicago University Press in 1992. And neutron stars are truly the gift that goes on giving. Peter's contributions not only illuminated the still poorly understood processes whereby pulsars radiate, but also the magnetars, which involve even stronger magnetic fields than typical pulsars, and probably the still more perplexing fast radio bursts. But Peter's insights ranged wider, and I should highlight an important 1975 paper on cosmology. This introduced what is now known as the Mészáros effect, the realization, very important for understanding emerging structure in the universe, that the amplitude of fluctuations in the baryons or dark matter doesn't grow if they're embedded in a universe where the dominant energy is radiation, which doesn't interact and doesn't participate in the clustering. A few more words now about neutron stars. As we all know, they were discovered serendipitously by Jocelyn Bell using a radio telescope, which was developed by Tony Hewish in Cambridge for another purpose, to identify compact radio sources, because they, unlike larger radio sources, would scintillate due to plasma fluctuation in the solar wind, just as stars, but not planets, scintillate, twinkle because of atmospheric fluctuations. So for that purpose, the telescope was specially designed to allow short time resolution. But of course, finding intrinsic variations in radio sources on sub-second timescale was the mega surprise. An interesting counterfactual, incidentally, is that if Hewish's telescope hadn't existed, radio astronomers may not have discovered pulsars. The first detected neutron star could then have been the one in the Crab Nebula, revealed by optical pulsations, or the one in Hercules X1, where an X-ray binary source with a regular 4.8-second period was discovered by the Uhuru spacecraft in 1971. But let's now turn to another phenomenon which was to play a big role in Peter's later scientific career and offered me the chance for extensive collaboration with him: gamma-ray bursts. These were, like the pulsars, a serendipitous discovery by American scientists using detectors designed to identify clandestine nuclear tests, which might have been carried out by the Russians in space. Gamma-ray flashes were detected in the late 1960s, but it took several years, until 1973, for it to be realized that they came from beyond our solar system and therefore were natural and not sinister. And a paper was published in APJ. The field developed rather slowly in its first decade because of the lack of sophisticated gamma-ray telescopes. But from the start, it was clear that these were interesting as examples of very extreme physics. When Mal Ruderman gave a review talk at the 1975 Texas conference, he noted that there were more theories than detected bursts. Progress, in the sense of adding more data and killing off non-viable theories, sped up after the launch in 1991 of the Compton gamma-ray satellite. Its BATSI instrument accumulated an all-sky sample of over 1,000 bursts. It revealed that they were more or less isotropic over the sky, and also that there were two main categories, long and short. But there was still a debate about just how far away these bursts were in the universe. Indeed, this topic was debated in 1995 in the Smithsonian in Washington on the 75th anniversary of the famous debate between Shapley and Curtis on whether the so-called nebulae were part of our own galaxy or whether they were much further away and galaxies in their own right. In this new debate, Don Lamb favored the local hypothesis, which meant that the gamma ray bursts were outlying objects in our own galaxy, and Boden-Paczynski argued the other way. And I was asked to chair this debate because I'd written papers on both sides of the argument. At that stage, it wasn't completely clear who was right, but the issue was settled soon afterwards by the Beppo-Sachs X-ray satellite. This instrument was able to detect X-ray afterglows from two bursts and thereby locate them in the X-rays with sharp enough angular resolution to reveal a definite association with distant galaxies. And that settled the great debate and indicated that the bursts emitted within a few seconds more energy than a supernova. My own collaboration with Peter on gamma ray bursts started in 1992. We developed the idea that the bursts were generated by jets expelled relativistically from a compact object. We were initially rather unspecific about that compact object, but a consensus emerged that there were, as I mentioned, two different kinds of bursts, and that the short ones resulted from binary neutron star mergers, and that the longer ones came from a kind of supernova triggered by a collapsing star which was rotating, so that the energy released during the final collapse of the core didn't diffuse out as a normal supernova, but squirted directly out along the minor axis, along the rotation axis, to produce a jet. This story, which involves relativistic jets, shocks, pair production, etc., has broadly survived, and it's been developed by many people at this conference and many others. And I'd like to highlight in particular the especially extensive work over the decades done by Zvi Paran and his colleagues in Israel. Fast forwarding now to the present, what's been important in the last 20 years in aiding our understanding of these violent events has been the extension of multimessenger astronomy to non-electromagnetic channels. As already mentioned, in the 1960s, the only two messengers were visible light, supplemented to some extent by the radio band. Space technology opened up the X-ray and gamma ray windows. But more excitingly, astronomers are now deploying two other quite different channels, neutrinos and gravitational waves. And Peter, in his later career, has been a key theorist in the so-called ice cube detector in Antarctica, which has been able to detect enough high-energy neutrinos to at least give us a crude map of the sky. It's hard to identify particular sources, but it's believed that some of these neutrinos come from distant explosions, which may also be the origin of the highest energy cosmic rays. Still another big mystery. And the second new messenger was gravitational waves. And it was a real breakthrough when a burst detected by the amazing LIGO coincided with a short gamma burst, indicative of a merging neutron star binary. What about the future? Those of us who get to age 80 naturally wonder about whether we can still contribute usefully. Scientists grow old in different ways. Many stop doing active research or find their skills overtaken by new techniques. But some lucky ones, like Peter, continue to contribute to subjects in which they have experience and expertise, and they also are able to inspire younger colleagues. But I should mention as a warning that there's another route which has been taken by some genuinely outstanding astrophysicists. Sufferers from this syndrome retain their intellectual curiosity, but lose interest in the routine scientists they can really do. They become intellectually isolated, and they overreach themselves by overconfidently entering fields where they've not got much expertise. And I'm especially mindful of this because two of my most distinguished predecessors at Cambridge, Arthur Eddington and Fred Hoyle, both took this path and rather embarrassed their friends and colleagues by what they did in their later years. And I had a brief worry about Peter when, in preparing these remarks, I thought I should check his newest papers on ADS. I found two papers on a radically new cosmological model, where the universe had started off as an exotic, dense solid. This perplexed me until I checked with relief that there was another from a university in Slovenia. It wasn't Peter. Which Peter, as we all know, has his feet still firmly on the ground, and he won't go that route. But let's hope he has many more years of contributing to the field of multi-messenger astronomy, which he's done so much to open up through his work on cosmology, on gamma ray bursts, neutron stars, and neutrinos. But I think Peter would agree that we theorists should all be rather modest in realizing that the exciting progress that's led to today's multi-messenger astronomy is owed more than 90% to exciting new technology, to improved instrumentation, and to more powerful computers, rather than to armchair theory. Peter has, of course, hugely influenced high-energy astrophysics through the students he's trained and the attendance at this meeting testifies to this range. So just a word for those here who are just beginning their careers. I started my talk by perhaps being a bit too nostalgic about the faraway era when Peter and I were starting, when there were exciting advances that rendered the experience of the old guys at a heavy discount. But I think those just starting now will be just as lucky. The rate of discovery isn't slacking. There are challenging new problems that those in earlier decades never envisaged and never had a chance to think about. Well, I've gone on for long enough, but before he speaks, I'd like to extol one of our middle-aged colleagues, Bing Zhang. His monumental treatise, here it is, tells us all that is known about gamma ray bursts. It's a treasured text for many of us in the subjects, and I mention it myself in case he's too modest to highlight it himself. So, although I may have gone on too long, I'm very glad to have had this chance to make these remarks and look forward to the rest of the discussion. Thank you very much.